So welcome back. Today we are going to see in this lecture video the discrete time state variable feedback topic, and along with that we'll be also seeing the design of observer and some theory of minimum order observer. Let us first start with design of pole placement. Okay, so pole placement design is also called as arbitrary pole placement or state feedback control. Okay, so what happens that in our traditional method we approximate the transient response specifications with dominant complex conjugate pole pair SD, and thereafter what we do that we design the system accordingly in time domain or frequency domain such that the SD is the part of root locus and it is meeting the time response or frequency response specifications. But there is one approximation in this design that we are considering that the third pole, if it is a third order system, it is not coming into the region of dominance, and due to that our response is satisfactory. But when we go to pole placement problem, the pole placement problem is taking into consideration all the desired poles and zeros, particularly poles of closed loop transfer function. And so we start with the assumption that the transient response requirements like rise time, settling time, maximum overshoot, damping ratio, bandwidth, omega n, or whatever are the specifications, they are met with the help of closed loop poles, and these closed loop poles we find out with the help of certain trial and error methods or certain guidelines. For example, we can approximate these rise time, settling time by dominant poles, and third pole will place at least 10 times, approximately 5 to 10 times to that of the real value. But we can exactly find out these poles and zeros locations with some trial and error on simulation software like MATLAB. Okay, so with such considerations we will consider that the closed loop poles will assume that the closed loop poles are at location mu1, mu2, mu3 up to mu1. So n number of poles they are at n number of locations, desired locations, and desired locations are mu1 to mu1. Before we start with the design of pole placement and see what is exactly pole placement, we'll see the necessary and sufficient condition for pole placement. Let us consider an open loop transfer function and a state equation in discrete time domain is given by x of k plus 1 is equal to g into x of k plus h into u of k. So for design of state feedback, the output equation is not needed. Y is equal to c into x of k plus d into u of k. That is why I have not written intentionally. And x of k is nothing but the state vector at the kth sampling instant, and u of k is nothing but the control signal which is a scalar at kth sampling instant. And the system matrix G is n by n matrix, and the feedback matrix H is n by 1 input matrix. Okay, so before we start with the pole placement problem, it is necessary and sufficient condition for pole placement is that the rank of the controllability matrix, that is nothing but H, GH, G square H up to G to the power n minus 1 into H is equal to n. So if this condition is satisfied, if the system is controllable, then only with the help of unconstrained input vector we can change from initial state to the final state, and we can go for the design of arbitrary pole placement or design of state feedback. Okay, So the design via pole placement is also called as arbitrary pole placement, because after the state feedback is designed, we can place the poles in arbitrary desired locations. Okay, so arbitrary pole placement means we are placing them at the desired locations. Okay, so this is what is the importance of state feedback, and this is the necessary and sufficient condition for arbitrary pole placement, that the rank of the controllability matrix must be equal to n. That is, the system is controllable. If the system is not controllable, we need not to proceed for the design of pole placement. Let us see this figure. Now this is the block diagram representation of the state equation. Z to the power minus 1 is nothing but unit delay. So z to the power minus 1 into I. So what this equation represents? X of k plus 1 is nothing but g into x of k plus h into u of k, right? And integration of x of k plus 1 is nothing but x of k. So z to the power minus 1 is the integration basically. So when it comes to discrete domain, it is nothing but the time delay, previous instant. Let us see the state regulatory system. First of all, we will consider what is state regulatory system. State regulatory system is the one where the input, reference input is equal to 0. For example, we can consider there are many systems which are having reference input equal to 0. Let us consider the inverted pendulum. The inverted pendulum has a bob in the upright position. And let us consider a 2 degree of freedom inverted pendulum. So inverted pendulum is nothing but it is a bob which is mounted on the stick in the upright position, and our problem is to maintain that particular bob in the upright position. That is, this particular angle, see, this is nothing but the bob, and this is nothing but your inverted pendulum. It is mounted on this cart, and this angle theta should be equal to 0. Okay, so this is what is the problem of inverted pendulum, that is reference input is equal to 0. So there are many regulatory systems, for example UPS and all, where we find that the reference input is equal to 0, and such systems are called as state regulatory systems. Okay, let us proceed further. So for state regulatory system, we are considering that R of t is equal to 0, and this U of t, that is input to the system, is nothing but minus k times x of k, where k we call it as a state feedback control matrix. Okay, and this is our system as we have discussed earlier. So this is nothing but the state regulatory system with state feedback. Let us see the state feedback control law. Now the magnitude of control signal u of k is chosen as u of k is equal to minus k times x of k. Okay, so this u is equal to minus kx is called as state feedback control law. So what is state feedback control law? U is equal to minus kx, where k is the state feedback gain matrix, which is a 1 by n matrix, and the system becomes closed loop control system, as will be showing in the figure, or we have already shown in that particular figure, and its state equation becomes x of k plus 1 is equal to, so we have to substitute u of k is equal to minus kx in the equation of x of k plus 1 is equal to g into x of k plus h into u of k. So we will get x of k plus 1 is equal to g minus h into k multiplied by x of k. So we should note that we can choose the matrix K such that the eigenvalues of G minus HK are the desired closed loop poles mu1, mu2 up to mu_n. Okay. So if we properly design the state feedback matrix K, then the roots of this particular characteristic equation can be placed as per the desired closed loop poles, because this is now the new characteristic equation. The earlier characteristic equation is modified with the help of the state feedback control matrix, and thereafter we can arbitrarily assign or we can assign the poles at the desired location with the help of this state feedback control law. Note, characteristic equation with eigenvalues, actual eigenvalues or actual characteristic equation is given by Zi minus G is Z to the power n plus A1 Z to the power n minus 1 plus up to An minus 1 Z plus An is equal to 0. If we compare this equation with the actual characteristic equation, we will get the value of A1 to An. And the characteristic equation with desired eigenvalues is given by Z minus mu1 into Z minus mu2 up to Z minus mu_n, which we can equate to alpha 1 Z to the power n minus 1 plus up to alpha n minus 1 Z plus alpha n. So this will give you the value of alpha 1 to alpha n. This will be needed when we solve the problems which is forthcoming. We will consider now an example for design of state feedback. Let us consider the system that is given by x of k plus 1 is equal to g into x of k plus h into u of k, where g is equal to matrix 0 1 minus 0.16 minus 1 and h is 0 1. The problem statement is determine a suitable state feedback gain matrix capital K such that the system will have the closed loop poles at Z is equal to 0.5 plus J 0.5 and second pole is at 0.5 minus J 0.5. That is, the desired pole locations are at Z is equal to 0.5 plus minus J 0.5. Okay, so first of all we will find out Zi minus G, that is the characteristic equation, actual characteristic equation. So Zi minus G will come out to be Z minus 1.16 Z plus 1. We have substituted the value of Z and I is 1 0 0 1, and we have subtracted this G from Zi minus G. It comes out to be, determinant of that comes out to be Z square plus Z plus 0.16. And here we will compare it with the characteristic equation of the standard system, that is Z square plus A1 into Z plus A2, and from that we will get the coefficients of the actual characteristic equation as A1 is equal to 1 and A2 is equal to 0.16. Let us first examine the rank of the controllability matrix before we start with finding out the controllability. In this case, the rank of the controllability matrix is equal to 2, because the determinant of HGH, which is equal to determinant of 0, 1, 1 minus 1, is coming out to be non-zero value. It is coming out to be minus 1. Hence the rank of this controllability matrix is 2, and we can proceed for the design of the state feedback. Okay. Therefore, the system is completely state controllable and arbitrary pole placement is possible. The characteristic equation for this desired system, let us consider for desired system what is the characteristic equation. Now we know the desired poles are at zero point 0.5 plus minus j 0.5. So that in turn desired equation is given by zi minus g plus hk is equal to, so z minus zero point 0.5 minus j 0.5 into z minus 0.5 plus j 0.5, that is coming out to be z square minus z plus 0.5 is equal to 0. And we will have to compare it with the equation z square plus mu 1 into z plus mu 2 is equal to 0, and for that mu 1 will come out to be minus 1 and mu 2 will come out to be 0.5. Therefore, with this, getting the coefficients of the actual characteristic equation and the desired characteristic equation coefficients will now demonstrate in three ways how we can find out the state feedback control matrix capital K. First method is by use of transformation matrix capital T. This particular method is useful if the system is given in controllable canonical form, because the transformation matrix T in this particular case turns out to be identity matrix. The state feedback matrix gain K is given by alpha n minus an, alpha n minus 1 minus an minus 1 up to alpha 1 minus a1 t to the power minus 1. The state feedback gain matrix K is given as K is equal to alpha 2 minus a2 alpha 1 minus a1 into t to the power minus 1, because it is a second order system. Now the given system is in controllable canonical form, so transformation matrix will definitely turn out to be identity matrix. But let us see how to find out the transformation matrix capital T. T is equal to m into w, where this T is equal to m into w, where m is the controllability matrix which is having specific form HGH in this case, and this W is having one specific form that I have given at the bottom right corner of this particular screen. So it is having this particular form where a1 to an minus 1 are the coefficients that are given by this characteristic equation of the system zi minus j, and for n is equal to 2 in this case, a of 2 minus 2, that is a1 and 1 1 0. So this is the form of the w, and if we substitute the values then, and if we multiply these two matrices, it will come out to be identity matrix. Okay, and we can directly write is I if and only if the system is in controllable canonical form. If the system is not in controllable canonical form, in that case we have to find out the capital T and it won't be identity matrix I. Now for this system K is given by alpha 2 minus A2 alpha 1 minus A1, which is equal to, so alpha 2 we have calculated as 0.5 and A2 we have calculated as 0.16, and alpha 1 is minus 1, A1 is also minus 1, so the final matrix K is 0.34 and minus 2. So this completes the design of the state feedback matrix gain K by using the transformation matrix capital T. Next method is the direct formula that is derived by Ackermann, and this is known as Ackermann's formula. Okay. So the desired matrix K is obtained by Ackermann's formula like this. K is equal to 0 0 0 0 1 n times, this is a n by 1 matrix, and this is your controllability matrix H G H G to the power n minus 1 into H to the power minus 1, and phi of G, where phi of G is having the standard form Basically, it is according to the Cayley-Hamilton theorem that every state matrix satisfies its own characteristic equation. That is, phi of g is g to the power n plus alpha 1 g to the power n minus 1 plus up to alpha n minus 1 g plus alpha n I. Okay, so referring to the Ackermann's formula, which is given by this equation, for second order system, k is nothing but 0, 1, h gh to the power minus 1 phi of g, where phi of g is given by g square minus gh, because our alpha 1 is minus 1 and alpha 2 is 0.5. So 0.5 into I. So let us substitute the values of g and I over here, and we'll get phi of g as 0.34 minus 2, 0.32, 2.34. And let us substitute the value of this phi of g into this particular equation. We'll get k is equal to 0, 1, 0, 1, 1 minus 1 to the power minus 1 into 0.34 minus 2, 0.32, 2.34. That will come out to be 0.34 minus 2. So we are getting the same solution which we have obtained using transformation matrix by using the method 2, that is use of Ackermann's formula. The next method is what we call it as direct substitution method, because we are directly going to substitute the value of k, which we will define it as k1 and k2, into the characteristic equation, and we'll compare it with the desired characteristic equation with the like powers of s. This method is very easy and is helpful only for the third and lower order system. For second and third order system we can use it, but for higher order it becomes difficult to use this particular method. So let us understand what is the procedure. Zi minus g plus hk, which is desired characteristic equation, we can obtain it as Za. This is Zi minus g plus h times kk. Here we are assuming it k1 and k2. So Zi minus g plus hk is coming out to be this matrix, and in turn we solve the determinant. So determinant is this value. Now let us see what is the actual desired characteristic equation. We already calculated it. So we'll equate it with the actual desired characteristic equation. So these are the desired roots. From this we'll get the desired equation, z square minus z plus 0.5, equating it to what we have got earlier. So equating the like powers of s, 1 plus k2 is equal to minus 1, and 0.16 plus k1 is equal to 0.5. So k1 is coming out to be 0.34 and k2 is coming out to be minus 2. And hence we are able to find out the state feedback gain matrix K by direct substitution of K1 and K2. Next is the example of deadbeat response. We have already seen the theory of deadbeat response earlier. Let me reiterate that particular theory. A system will exhibit a deadbeat response. So deadbeat response is that response which gives output in minimum number of sampling periods without any intersampling oscillations. So deadbeat response is executed if the closed loop transfer function of the system is of the form 1 upon z to the power n. Let us consider the example which is given earlier. For second order system, we have to determine the state feedback matrix K such that the control law is given by u of k is equal to minus k into x, and the system will exhibit deadbeat response. So when we say the system exhibit deadbeat response to initial state x of 0, we'll assume that the control signal u of k is unbounded and the values of mu1 and mu2 will be 0, because the desired characteristic equation is z square only, and that is why rather than mu1 mu2 I should say alpha 1 and alpha 2 will be equal to 0, and if we refer back, then we'll get k is equal to here alpha 1 and alpha 2 are 0, so minus a2 minus a1 t to the power minus 1. So we are using the transformation matrix. T is equal to I in this case because it is controllable canonical form of the form 0 1 minus 0.16 minus 1, and the characteristic equation will be given by zi minus g is coming out to be z square plus z plus 0.16, and that will equate it to z square plus a1z plus a2 to get the values of a1 and a2. This is actual characteristic equation, and from here we get k is equal to minus a2 minus a1, that is 0.16 and minus 1. Okay, so if we use this transformation matrix K, in that case we will get the deadbeat response. Next topic we are going to cover is discrete time state variable observer. So till now we have considered the state feedback matrix K design, but now we are going to see the analogous problem which is called as state variable observer, design of state variable observer. What happens that up till now we have considered that all the state variables are measurable, but in practice it may happen that the state variables are not measurable. If state variables are physical variables, we can measure them, but if they are canonical variables, if they are control phase variables, in that case it is not possible for us every time to measure the state variables. Okay, so for design of state observer, so we have to design a state observer that in turn will take the input vector, and from output vector it will estimate the state feedback matrix x of k. So in what follows, we first discuss the necessary and sufficient condition for the design of full order state feedback. So for full order state feedback matrix, the rank of the matrix C g to the power n minus 1, C g to the power n minus 2 up to C should be equal to n, which is equivalent to rank of C transpose G transpose C transpose G transpose to the power n minus 1 C transpose should be equal to n for the nth order system. That is, the system must be observable. If we could observe the system state variables, in that case we can design the state feedback matrix, or we can design the state feedback matrix gain k with the help of observer, and for that the system should be necessarily observable. This is the diagram of the full state order observer. This is called full state order observer because we are observing all the states. We are observing all the states. So this is in general the block diagram of the observer. But here we are considering that we are able to measure all the state x of k. But observer is the one which is shown in the next figure that I am going to show you right now. Let us consider the state feedback control law which was given in earlier figure. X of k plus 1 is equal to g into x of k h into u of k, and y of k is nothing but c into x of k. D we have ignored because D is direct transmission matrix. Most of the times there is no link between input and output, and that matrix D becomes 0. Okay, so the state feedback control law, as we have seen earlier, is u is equal to minus kx, where x is the state vector, u is the control vector, y is the output vector, g is the non-singular state matrix and man, and h, c and k have their usual meanings. Now we assume that the system is completely state controllable and completely observable. But x of k is not available for direct measurement. Okay, so we'll shortly see the figure 2, and what we'll see from that particular figure is x of k plus 1 is equal to g into x of k plus h into u of k plus ke into y of k minus y of k desired, that is y tilde, we show it here in this case. So basically ke is nothing but the state feedback gain matrix, which is n by m, and the last equation we can modify it as x of k plus 1 is equal to g minus ke times c into x of k plus h into u of k plus ke times y of k. This is that particular figure. Here is our system represented in the form of state model. Here is the output y of k. This is nothing but our observer, state observer. What state observer will do? It will, from the input and from the output, for a particular input, this estimator will estimate the state x tilde of k, and when it is given as input to C, it will calculate y tilde of k, and that in turn will calculate the error, and this error has to be multiplied by the matrix ke, and we have to once again put this particular error into this system, and so this is the error dynamics. X tilde of k plus 1 is nothing but gx tilde of k plus hu of k, where x tilde indicates the estimated state variable. And to obtain the necessary observer equation, first of all, if x is equal to x tilde, then the response of the state of observer will be identical to the response of the original system. And for that, the observer equation will be obtained from the error equation. So x of k plus 1 minus x tilde of k plus 1 is nothing but g minus kec into x minus x tilde. That is nothing, this is nothing but error. So ek plus 1 is equal to g minus k into c e of k, and if what we want, that the dynamic response of the system should be improved, and if this matrix G minus KEC is stable, then the error vector will converge to 0 for any initial error E of 0. Okay, so this is dynamics behind that. So we have to design the matrix KE such that the desired dynamic response is obtained and error should tend to 0. First method is use of transformation matrix capital T. The state feedback observer gain capital E can be given by this equation: q into alpha n minus a n alpha n minus 1 minus a n minus 1 up to alpha 1 minus a1, and q in turn we find it by w n conjugate, where n and w are we have defined earlier. N is the controllability matrix, w is having some specific form. The alpha i's of the coefficient, alpha i's are the coefficients of the desired characteristic equation, which is given by this particular equation we have already seen earlier, and ai's are the coefficients of the characteristic equation of the original state equation, that is zi minus g is equal to zn plus a1 z to the power n minus 1 plus an minus 1 up to an minus 1 z plus an equal to 0. Now if the system is already in observable canonical form, then matrix KE can be easily determined, because in that case Wn conjugate will become identity matrix and Wn conjugate inverse will be also equal to I. So this is the first method. Second method is by using the Ackermann's formula. The Ackermann's formula for observer gain feedback is given here. K is equal to phi of G Cg to the power n minus 1 whole inverse multiplied by 0, 0, 0 up to 1 n times, and phi of G is nothing but the G to the power n plus alpha 1 G to the power n minus 1 plus alpha n minus 1 G plus alpha n I. Next method 3 is direct substitution. Of course, we can, if the system is of lower order, then we can have assumption on observer design gain matrix Ke, and we can find out the elements of Zi minus G plus Kec, and we can equate it to the desired characteristic equation where mu i's are the desired eigenvalues, okay, mu1, mu2 up to mu of the characteristic equation G minus Kec. Equating the like powers of Z will give you the value of Ke coefficients. Let us consider one example. Here we will consider the example and solution by direct substitution method. So the problem statement is like this. The system is given to you and values of G, H and C are given. This is same problem, and design a full state observer assuming that the system configuration is identical to that of shown in the figure 3, and the desired eigenvalues of the observer matrix should be at 0.5 plus minus j 0.5. Now the desired characteristic equation is this, and from this we will find out the values of alpha i's, and the rank. First of all, we have to determine the observability matrix. So observability matrix is C transpose into G transpose. That is coming out to be 0, 1, 1, minus 1. That is the determinant is equal to minus 1. So system is stable, or rather the system is observable. So we can go for the design of observer. And we already seen the system is controllable as well. So we can proceed. And here we will have to find out the error response, which is the difference between x of k minus x tilde of k, and the characteristic equation of the observer is Zi minus G plus Ke is equal to 0. Let us denote the observer feedback gain matrix Ke as K1, K2 as a column matrix. Then the characteristic equation Zi minus G plus K times C is coming out to be this, equation number 8. And the desired characteristic equation, we already found it as Z square minus Z plus 0.5. So equating the like powers of Z, will get K1 is equal to 0.34 and K2 is equal to minus 2. Therefore, K is this particular matrix, which is nothing but the observer matrix. Now let us see the theory of minimum order observer. Minimum order observer is an observer. In most of the situations, it is not always recommended or required as well to measure all the state variables or to estimate all the state variables. Some state variables are measurable. Okay, so what we can do is we can partition this state vector by two state vectors. One is for xa of k which is m vector and xb of k which is unmeasurable portion. So xa of k is the measurable portion and the remaining is unmeasurable, and this partition state equation can be written as xa of k plus 1 is xb of k plus 1 is equal to GAA, GAB, GBA, GBB into xa of k, xb of k plus HA, HB into u of k. This particular equation is called as partitioned state equation. And this is nothing but the minimum order observer. So for minimum order observer, once again we take the input u of k, y of k, and we have certain transformation with the help of y of k, and we estimate x tilde of k, that in turn will multiply with the state feedback vector, and in turn will provide as input u of k. So this is the schematic diagram of minimum order observer, and these are some dynamics. X of this is our system and this is our partition matrix, and our control law is u of k is equal to minus kx, and we have to transform the state equation into partitioned state equation, and we have to do certain substitutions. The substitutions are x of k we have to substitute as xb of k, g of k we have to substitute as gbb, then h into u of k we have to substitute by this particular expression, y of k we have to substitute by this particular expression, c we have to substitute by this particular expression, and ke n by m matrix will become ke n minus m multiplied by m matrix, and we can solve the design of state observer in a similar way that we did in case of full order observer by substituting these terms. And with this, we have covered the theory of minimum order observer in short, and these are the reference books: Discrete Time Control Systems, second edition by Katsuhiko Ogata by Pearson Publication. And thank you so much for watching this particular video, and I hope that this particular video lecture must have given you a quick start of how to understand the theory and how to solve the problems with the design of state variable feedback and the design of observer. Thank you.